Hello guys and girls, welcome to the computing workshop. I am the mad computer scientist and this is my workshop, and today we are looking at some next part of our scratching the surface of the Go programming language. And we are going to discuss some concepts. Today we are moving into the more advanced parts, and we are going to look at closures, which is a concept that Go supports. We are going to look at records or data structures, how to declare them, and how to attach methods to them, which is something that Go also supports. You can attach methods to data records. We will see how this works. You have. We will also look at iterations and collection types, initial collection types, which is the array, and the slice type, and what that is. Without further ado, let's start with looking at closures. Now, if you haven't heard of the concept of a closure before, it means that you can return anonymous functions. A function itself is a first class item or object in the programming language and environment. It means you can return a function, and that function will then close over local variables. What that means we'll see by looking at an example. So I have an example here. Go supports closures fully and anonymous functions, which we will see. So let's start by pasting some code here. Whoop, and that's interesting. So let's rearrange this. If we save, does it? Yeah, okay. So let's fix that. So now our imports got deleted, of course, because yeah, okay. The linter deleted the imports I had added, but never mind. So okay, so I've written a small method here for testing. We're showing you what the closures, what it means and what it does. So this function here, called test closure, will take in a string parameter called counter type. So this will determine this is actually just we will count up and we will count down depending on the type that we send. We can send incremental or decremental. Here you can also see that Go supports the switch statement. So here we can switch on counter type. We can use the switch case statement just like it's like we can in C. However, and then we have default case here. And this is just like C syntax. So we send in and here we declare a local, I declare a local variable here, which is local to this scope, right? This function. And this is where we will see what will happen when we have a closure, because now you can see that in either case we return a new anonymous function, and this is declared like this. We return a function which in turn returns an integer. So here we declare the function itself in the return statement. This is entirely anonymous. This function isn't named anything, and it cannot be called on its own except by this returned reference to it. So this is actually a function within a function. Okay, so this is an anonymous function. and we return this anonymous function, and we can then use that to call. Now, the instance of the variable here, which we are manipulating in this function, this instance of counter. Now, you would expect in a language that doesn't support closures that you have this is only local to the each call of this function, right? However, now that we return this anonymous function, a separate reference to a counter, this variable will be local to this returned function. So this will actually be and this is known as this thing closes over this variable, and suddenly there exists a unique instance of this counter variable. And what will happen when that when that takes place, we will see by introducing our main method. Give me a second. Here we go. We'll save that so that it fixes the. Okay, probably not. Let's see what's going on here. Let's remove this one and now save it so it fixes the. Yeah, okay. Now we need an import as well. So okay, so it actually fixed the linter, fixed our imports again. That's great. Okay, so now to show you what will happen here, I will create. I will set an implicit variable here that will be given the result of the call to test closure, this method, which we know will return an instance of, or it will return this anonymous function. Okay, and we can see that by hovering this, we can see that this actually returns. This is now actually given the type func int. So this now refers to a function that returns an integer. And then we can see when we print this, we print the first time we run it, and then we run it again, this reference, not the test closure reference, because this returns the actual function. So these close over this counter variable, which we will see when we run it. And then we create an entirely new instance of this func with a new closure over the value, which we call inc2, and then we print that one as well, and you will see what's going to happen. So now there will exist several instances actually of this, several unique instances, because these will close over this previously local variable. This variable is actually still local to this function, but this is a closure over this declaration here. And what happens is, by these anonymous functions, you can also use, by the way, you can also pass anonymous functions as arguments. You can pass something like this into as a parameter as well, as an argument, and that's fine. So now, or you can even pass if you have something, if you declare that you're going to take in an argument which is a func int, you could also pass this, for instance. This is how you can do this. This makes it very easy to do callbacks. For instance, you can set up your callback methods by allowing the caller to also pass in their callback methods, which is very useful in for instance in web programming or in distributed programming in general, where you can send in your own callback function that you want to get called when something happens. So when that event happens, you've already you can just refer to, you can use the function that was sent in as an argument. That's that's a bit overkill for this discussion, but it's very, very useful in distributed programming. So let's run this first to see what will happen. So first let's build it. Sorry, got to go into the right folder as well, and this one is called. And now let's build it on the terminal like this, and let's run it, and you will see what happens. So you can see we start with counter being uninitialized, so counter is 0. Okay, because it's automatically initialized to 0 because it's an integer. So we call the first increment from this instance. Okay. And we receive 1, and then we call the first decrement and we receive -1. Now how could this be? Wouldn't, if this were the same variable being used, this local variable declared in this function, wouldn't it be 0 for each call then? Okay, so let's go on. We increment a second time by calling the same reference here, and we call the same dec reference. Now you see it's 2 and -2. So what's going on here? Wouldn't it be 1 and -1 again? You would expect that if you haven't seen closures before, because this is a local variable, right? So each function call, you would expect this to be reset again, initialized again. It's local to the scope. But however, as the functions that we are returning are closing over this variable, they actually, this thing that we are returning has its own reference to this. So which we can also see when we do the new increment reference here by calling test closure and getting a new anonymous function back. You can see that then all of a sudden it's 0. Okay, so you see that these are all referring to different and you can see that it's now 0 because we called it with increment and not incremental. So this falls back to the default case, which will only return the raw counter here, which will be the unaffected, the initialized variable as is, because it's not, nothing is done to it. It's just returning the counter, so it will be 0. Okay, you can see that this means that there exists a new instance of this that wraps or closes over this type declared here with its own reference. Now these have their own references, the increment and decrement, so these two have their own references to this counter variable and closes over it. Now this can be a quite a tricky concept to grasp, but the more you experiment with this, just think of it like if you have a C background, you are probably you're thinking about local scope here, right? But think of the closure like you are suddenly receiving a new reference somewhere to this type, which is unique for wherever you are closing over it. So this returned anonymous function, for instance, has a unique reference to this this variable, which is actually contained in a different scope, which is, so it closes over this, hence the name closure. And you can use Go supports closures, and this is also very good for different types of design patterns, which where this is very useful, which is why Go supports closures. Okay, so now we are going to move on to the next item. So proceeding to structures in Go. Now Go isn't a object-oriented language like C++ is. It's like C is, instead it supports data records or structures, which are ways to gather variables together, or gathers data into a record of some sort, like person or employment or file or things like that. So these are records of information that you can create, and you can pass them around in your program just like you could in C. The syntax for that is very much like C. However, it also supports adding functions to structures in a way that resembles sort of methods in object-oriented languages. With the syntax, it ties a method to being used implicitly on an instance of a specific structure. You will see this. I will show you this in this example, which is a very nice feature of the language. Um, so, and this is even more useful when we come around to talking about interfaces later on, where you can tie functions to implicit instances of an interface, because Go supports interfaces in its own way. It supports interfaces. You will see that probably in the next video session. We will talk about interfaces in Go. But now to talk about structures. So first I will paste some code here, and here you can see if we save this one, so we get the get one of these too many, so I'll do this. Here we go. So we can see here that this is a structure. So we start with the keyword type, and we're defining a new type. We call this type file data, and file data is this is very much like the type def keyword in C. So then we say that this is a structure containing the following data, and these are variables. So we have variable data contained within this structure. So here we have an integer called size, of a string called name, and we have an integer called access, and probably several others if this were to be a real data type. I actually took this from one of my backend programs that I created for some client some time ago, but and omitted a lot of other crap that was declared there. Just to give you an example of this. Now, once you have a structure, you can create structures for basically anything when you want to group data together, just like in C with the struct and type def keywords. You can see this is very similar. But now, Go supports adding functions that work on an instance of the structure. So let's see what I'm really talking about here by pasting another section. Let's see that these are correct. Yeah. Okay. So here, for instance, we say that we create a func, and this you can see here. We take a pointer to file data. Okay, and we call this function print file name with no parameters. You see this thing within the parentheses ahead of this will tie this method to a pointer to an instance of this, and then we can run this function implicitly accessing that instance through this pointer. We will get this pointer. This is like this pointer, sort of, if you want to use object-oriented terminology. This ties this function to an instance of a file data structure, and then we use this name, this identifier, to access one of the members of this record, one of the data members. This can be done, and this is also how you can do getters and setters. If you're like from the Java world, or C#, or even in C++, it's very common to have getters and setters. You lock down access to a class with like private or protected or something like that, and then you use getter and setter methods to manipulate the internal data so that you don't have to expose the internal data of an object. And this you can do with this. You can do basically the same thing if you're a bit clever. You can tie getter and setter methods here, and you can restrict so that these cannot be set from the outside. You can have getters and setters. That's a bit ahead of this discussion, but you could do getters and setters in Go. Even if Go isn't an object-oriented language, you can do them on the structs by using this type of construct here. So this is a func that works on this type of data. And now if you hover this, you can see what this is. And even if you hover, I think this one, you can see, yeah. Okay. So to try this one out, this is also the way you can attach. This makes it much easier to group functions that then get grouped to these instances. Any instance that is a file data will have this method accessible, and it will take that actual instance and use within the function. So instead of passing it as a parameter, defining it as a loose function like you would in C, you can actually tie these down to only being accessible through an actual file data structure, which will then be passed into the function, which is what is happening here. So if we then take some test of this, like this, if we save the file, we can see we have one too many of these. So if we do this, it should look better. So now in this test, we are just here we can see how to initialize a structure. So we can do like this, and we can have this implicit declaration that we've been talking about, the colon equals, and then we say file data, and then we have these. And within these we have named parameters, right? The ones we don't want to have a default value, we pass the name of the member, the data member, and the value, followed by a comma, and then the name, and then the value, and then the comma, and then the name, and then the value. This will implicitly create a unique instance of a record, file data record, with these member values, and put that in F, which we can now see that F is of type file data. Should declare it here. Now if we print it, you will see that, then we will print only the name, and then we will call this method here that we tied to. As you can see now, if we do this, you can see that this is now a function explicitly tied to F, because F is of type file data. If you cannot do like in C, you cannot. There is no function print file name like this that you can call. You have to call it through this, something of type file data. This is a very clever part of the Go programming language. It's very useful. So now let's build this just to show some examples. Let's see. There we go. And by doing this, we can see that if we print the full object, we will get it like this. Our object, we will print the full record. We get this. And if we print only the name, which is a dot, so we can access the members, just like you would in C, or for that matter in C# or Java or C++ or whatever. If you had an object, the same syntactic notation, you get the name. And now if we print from the attached function, we are now in here, and we can see that we also get access to that specific instance's name, because a pointer to that is passed in, and the pointer is automatically dereferenced in the case of a structure. So we can use the dot notation directly
This is a very, very interesting construct, this one. And that's it for structures and functions tied to structures and data records. Okay, so for the final part of this video, let's discuss the concept of arrays in the Go programming language. If you have programming experience, you're surely familiar with arrays, like sequences of data and indexed sequences of data, and we're going to look at a concept known as a slice, which is a view on top of an array. Now, Go doesn't really support that many types of data structures built into the programming language, the environment itself. It provides basically three building blocks. These are arrays, slices, and maps. And we will look into maps later on. Basically, there are key value pairs, lists of key value pairs. But then you have arrays and slices. And slices are views on top of arrays. So they are backed by an underlying array, but there are some functions working on slices that allow you to use them like lists, like appending and so on to them, which you cannot do with an array. But the Go programming language only has these three very basic building blocks, with the assumption that any other type of structure, like the various types of trees or branching trees or graphs or whatever it may be, any other type of data structure or representation may be constructed from these building blocks and functions working on these building blocks. So the language itself only provides the basic necessities for designing basically any other data structure or data collection type that you may need. But yeah, so arrays work like you would expect. If you come from like a C background, let's have a look at those. Let's paste some code. Looks like this. You declare a variable, right? And if you don't specify the syntax, if you don't specify the number of positions on the array, you get a slice. So then this would be treated as a slice. Now it's treated as an array with three elements, right? And then it's 0, 1, and 2. So indexing starts at 0. And you can add stuff to it. You can also read what is in this position. So this is an array containing three data elements, three string elements, like you can see here. This is quite straightforward. If you have any programming experience, it works basically just the same as it would in C, for instance. However, if we paste this code, and this is a slice, and we will get a warning that it says this is, as you remember, illegal in Go to declare a variable and then not use it, but we will use it eventually. But now, a slice is a view on top of the array. So we can either declare it on top of an existing array. So the slice is, here we are saying that we want something called a slice, and we want to directly assign this to this array. We want this array to back this slice, okay? So the array is backing the contents for, it's supplying the contents for the slice. So the slice is a view upon this. And we say that we want to have a slice which covers only index 0 up until index 2 minus 1. So this is two elements, 0 and 1. This is how this works. This is the starting index, and then this is the ending index, but you get ending index -1 in this case. So you get between index 0 and 1. Okay, and this is all we can see. It's still this array, so we have to remember that changes to the underlying array will affect this slice, because this slice is just a view on top of this array here. Okay, and vice versa. We can use the slice to alter the underlying array. It becomes a view on top of this array. So now we can get the array, the backing array, created for us by creating a literal slice. So we can do this. We can say that another slice is, and this is the slice type, is the empty brackets, unlike the array declaration, which has a number of positions. Here this is a slice, and then we say that this is a slice of string, and then we pass in 2 strings. So now this will create an array for us, which we can only access this array now through this slice, because we create a literal slice. So it still needs a backing array, but the compiler will create one for us, and then this will refer to that array that was created. Now paste some more code. Now that we know how slices work and arrays, we can also look at something that you most often will use with slices and arrays, which are iterations. Now, the Go programming language has one type of iteration primarily, and that is the for construct, which you probably know from C. It looks like this. So here we say that we have our iterator variable, which we call I, and we set it colon equals. So we start by assigning this to 0. This will default to type int because 0 is an int, and then we iterate while I is less than 3, and for each pass of the iteration we add 1 to I. So this will print the index there. So our target here is to print the contents of this array. So we will go 0, 1, 2, right? But what you can do is the Go version of for each. If you are familiar with C# or the Java for each notation with colon, this is the same thing. It's called a range. So this will, but it will also pass back. This is the range keyword. This is actually a multiple return, like we saw earlier, because now we're saying that for x and y, which are colon equals, these are 2 returns from when we say range on another slice. Now you will see what will happen. X is an int. This is the index that we're at, okay, in the range across this entire slice, this view on top of the array. So start at 0, and for each pass it will increase to the next, and this is the index. But we will also get back, here you will see that y will in this case become a string, because we will actually get the value at that index as well. So we can directly print y, because y will be the string at this index. So this is a multiple return, which happens in cases usage of the range keyword. And this is actually quite handy, because you get the actual thing at this position, right? So and this will then automatically become of the type that is returned. We're using the colon equals, so we will automatically set this. In this case, this will become a string, because this holds strings, right? It's a view on an array that holds strings. So let's paste some more code like this. Okay, so here we can see now a function that uses a slice. So now we will say a slice. We created this one, and this a slice is a view on top of our first array, which contains 3 strings. So and here we say that we want to use this slice to add 3 more elements, and you will see what will happen. This will actually, now if we then print, if we go across this slice, we will ignore, we don't have a view on the third element. We have a view on 0, 1, 2, or 0 and 1, index 0 and 1. But now, since this cannot hold the if the underlying array cannot hold the values that we add, we will implicitly create a new array which will be returned from this function. So we set a slice to point at this new array, which will contain the initial contents plus whatever we're appending. And the append function is a built-in function in the Go programming library, standard libraries, and it takes a slice. So this is, you can use a slice here, but not an array. So this is, you have a slice as a view on top of a backing array, and you can use the slice to append. So you can call the append function with a slice, and you can append values to it. Then we use the same range iteration here, but across this slice here. So we will get an int, which is the index, and we will get a string, which is the actual value, and then we use that to print just like we did here. And this should be basically all there is to it. Now if we go into this and we do a build like this, whoops, we type like this. Okay, so here you can see the first printout is just the standard for iteration, use the standard iteration with a named variable. So we go an indexing variable, so we go print this entire array, since index 0, 0, 1, 2, and then we print this slice here, a slice, which happens we print our literal slice, rather, this one, another slice. So we print this one, which is how the planet, it has this one has the anonymous backing array, which we can only access through this slice variable, and then we use the append function to append to a slice, which now is a view. Initially it's a view on this, so it contains hello world, but not again. Remember, we only have a view on index 0 and 1, so we have an index between 0 and 2 minus 1, so between 0 and 1. Okay, so what will happen is that it now has a view on the first two of these. It has a view on hello and world, and then we tell it to append these ute, woot, and bruh statements here. So we get back a new array because it couldn't, the initial, it couldn't hold these values. So we get a new anonymous array and we assign it to a slice. And then when we iterate over that, we can see that we retained the first ones we had a view on, and then we also appended the ute, woot, and bruh statements. Okay. So this is how you can work with arrays and slices, and then you have to remember to use slices in functions like append, so you can actually use it like a list. In other programming languages, for instance in Java, this is a typical array list. This is the thing happening here is very much similar to an array list. You have something on top of a backing array. The array is the backing raw data structure, but then you have, in this case, the slice is the view on that, and it's the view that you use to pass around to methods and so on. And this is the way to iterate then, either by the named variable or by the range, the range construct, which is a multiple return, as we were discussing. And that is basically it for this video. And in the next video we are going to look at maps, and we are going to look at interfaces, and then we are going to look at the multi threading, the parallel execution parts of the Go programming language, which is one of its biggest strengths, with Go routines and channels for inter-process communication. Okay, and that will be the last one of the basic Go programming language overview videos, and then we will actually construct a small web service to show the language more in action. So see ya.